Let's go back to the alphabets, words, and so forth, and talk about the set operations with sets of those. So here we're going to consider sigma, our alphabet, to just contain the set of A and B. We're going to consider the set A to contain the words lambda, AA, AA, and AAA. The set B to contain the words lambda, B, double B, and triple B. And set C to contain all the words in sigma star such that the length of the word is less than or equal to 2. Now we can list out the elements of set C real quick. That's all the words of less than or equal to 2. So lambda, being that that's length 0, would be part of that set. It would also include single A and single B words, plus the words of length 2, which would be AA, AB, BA, and BB. Now let's consider some set operations based off of these. Let's do A complement with B. Now we take everything in A and remove what it has in common with B. There's only one thing it has in common, and that's lambda. So if we take away that, all that's left is A, AA, and AAA. If we look the other way around, B relative complement with A, well, same idea. The only thing they have in common is lambda. So if I take that away from B, all that'll be is the B, double B, and triple B words. If I look at A intersect with C, let's look at what A and C have in common. They have lambda in common. What else do they have in common? They also have an A and AA words in common. So that would be the intersection of those two sets. If we do C relative complement with A, we'll take everything from A that's in C and take that out of there. So we just figured out what they have in common are those three things. So if I take the lambda, the A, and the AA away from C, what's left over is B, AB, BA, and BB. If we look at the B complement with C, so if we take away from B the stuff that it has in common with C, that's going to take away the lambda. They also have a B. That B will get taken away. The double B, well, that's also in C, so that gets taken away. So all that would be left over is BBB word. Lastly, A complement with sigma. Okay, sigma is just, again, our set of our alphabet containing A and B. So if I do the complement with sigma, that means I'm going to take the stuff from sigma away from A that it has in common. There's only one thing that they have in common, and that's the single letter A. So if I take that away, it'll leave me with lambda, AA, and AAA. Here's a question that says, does A union with B equal A union with C mean that B equals C for sets A, B, and C? Now, in a previous part of the section, I showed all the different properties of set operations, and we know those will work okay. This one seems like it could work, because if you're taking the same set A and you union with B and union with C, and they're equal to each other, that might be suggestive that both B and C are equal to each other. However, let's see if we can find a counterexample that shows that this is not true. So let's just take a look at a set A containing the elements A, B, C, D, and E. Another set B that contains the elements of D, E, and F. And another set C that contains the elements A, E, and F. If I take A union with B, what would that be equal to? That would be taking everything with A and B and joining them together. So it would look like A, B, C, D, E, and F. If I do the same thing, A union with C, then I'll have A, B, C, D, E, and F. So indeed, it shows that these are equal to each other. The A union with B and A union with C is equal to each other. However, B and C are different sets. They contain different elements. So this shows that our statement is actually false. So in other words, we can have two unions that are equal to each other like this. Doesn't necessarily mean that any of the sets are equal to each other. We'll wrap up our discussion in this section with looking over the definition for ordered pairs. It says, consider two sets S and T. For each element S in set S and each element T in set T, we form an ordered pair of S, T, here denoted by S, T in parentheses. The set of all ordered pairs is called the product for S and T and is denoted with S, looks like the multiplication X, with T. I pronounce this S cross T. S cross T is equal to the set of all ordered pairs S, T, such that S is an element of S and T is an element of T. This is a generalization of the ordered pair notion from things like the XY coordinate system, but now in generalized set notation, our components of the ordered pairs can be any objects whatsoever that we have defined within our sets. In this case, you can see how this is going to work in this example where our set S contains 1, 2, 3, 4, and set T contains letters A, B, and C. We're going to find S cross T and S cross itself, or S squared. And also we're going to find the set of all ordered pairs X, Y, and S cross S, such that X is equal to Y. What I like to do to construct ordered pairs is to draw sort of a table with the elements from each set to help kind of keep things organized. So elements from S are 1, 2, 3, and 4. Elements from T, A, B, and C. So we're going to do S cross T. So what that means is the first element of each ordered pair will be a number from S, and the second element of each ordered pair will be an element from T. So in the first set of ordered pairs, let's say we have 1, A, 1, B, 1, C. Putting together the 1 from S with A, B, C from the set T. And then we'll also have a 2, A, 2, B, and 2, C. 3, A, 3, B, 3, C. 4, A, 4, B, and 4, C. These will be all the ordered pairs contained within S cross T. So we'll write it here with all the ordered pairs together as the set of ordered pairs. So I'll just write them out here. Okie doke. And so in set notation, this will be all the elements of the set of S cross T containing those ordered pairs. If we look at the set for S cross itself, or the product of S with itself, I'll do a similar thing with the table, taking the elements from S, combining it with ordered pairs with other elements in S. So we'll get ordered pairs like 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, and 4, 4. Okie doke. Those are all the elements here listed out in the set for S cross S. So now we're going to look at the set of all ordered pairs X, Y within the product set of S cross X, such that X is equal to Y. Well, looking up above at the elements of S cross S, we're looking for the elements where the first part and the second part of the ordered pairs are equal to each other. So, for instance, 1, 1, 2, 2, 3, 3, and 4, 4 all have first and second elements equal to each other. So those would be the elements of our set. It would be the set containing the ordered pair 1, 1, 2, 2, 3, 3, and 4, 4.